So what happens when a nucleus becomes more stable by giving out alpha particles? So the first thing is what is emitted. So the type of decay is alpha decay. What is emitted? It's an alpha particle. The description of the decay then. So I'm just going to write in here, it's also similar to a helium nuclei. So we have a helium nucleus, or the equivalent of a helium nucleus, which is 2 protons and 2 neutrons being emitted from the nucleus of whatever atom is unstable. So the effect of the decay on the nucleus, and the effect of the decay on the nucleus is that it changes the nucleus. And just down the bottom we'll say a wee bit more about that. It changes the nucleus. And so it becomes a different element or a different atom. Now, we very often fill in an equation, and it might be a decay equation. So here you have uranium 23892. I'll maybe scan in that a wee bit for you, if this works. Yep. Okay, so we have 23892 uranium, and we're told here that it's decaying to give you 23490. Now the atomic number has changed, the number of protons has changed, so this is now a new element, and the element which has a mass, an atomic number of 90 is thorium, Th. Its atomic mass number has also changed. So I'm going to write in, I know that in this case it has given out alpha, and so it's got a 4 at the top and a 2 at the bottom. And there will probably also be some energy emitted as well. So if you have a wee look at those numbers, just like a chemical equation, the numbers should add up to give you the same value on the right hand side and the left hand side. So 92 is the value on the left hand side here at the bottom. So 90 plus 2 gives you 92 on the right hand side. 4 plus 234 gives you 238, and that's the same as the number on the left hand side. So what has happened to the atomic mass number, which is the top number? It is decreased by 4. And then the Z number, or the atomic number, has decreased by 2. And you can see these is kind of written mathematically here, A minus 4 and Z minus 2. You don't really need to remember that, but sometimes you might be given this, if I just cover that up again, and you're told that it decays by giving out a nuclear particle. What is it? So you can see that this is decreased by 4 and this is decreased by 2. And so you'd have to have a 4 here and a 2 here to give you 238 and 92 over here, and therefore this has to be an alpha particle. Okay, beta decay then, and I'll just scan out again so you can see this. So in beta decay, what is emitted? So you can see I've just got one wee circle here, and that is a high energy, and it's electron. So description of the decay. And what happens is actually a neutron in the nucleus decays into a proton and an electron. And I'm going to write this down. You don't have to learn this, but this is what happens. A neutron decays to give you a proton plus an electron. So this is a neutron in the nucleus. Now, a neutron has no charge at the bottom and a mass of 1. Okay, so if we were to write a neutron the way we wrote our alpha, beta and gamma particles, it's got a large mass, so a mass of 1 and no charge. A proton has got a mass of 1 and it has a charge of plus 1. So 1 equals 1, that's okay. Naught doesn't equal 1, so we must have a minus 1 here and a naught here, and then it's a beta particle. And that's what a beta particle is. It's a very, very high energy electron which is emitted from the nucleus. You don't need to learn this, but it is a good idea to understand where it comes from. Okay, an example of the decay might be something like this. 14.6C plus 14.7N plus. Now it's a naught minus, it is a beta particle which is being produced, so I'm going to write naught minus 1 in. So naught plus 14 gives you 14, minus 1 plus 7, or 7 minus 1 gives you 6. Be very careful about this kind of decay. It's really tempting to put in plus 1 there on this side. It's very tempting to do that, but that would be wrong. And if I just cover that up there, again, you could be asked a question, what is being emitted here? I should scan in a wee bit for you, I suppose. What is being emitted here? Well, you can see that this hasn't decreased. A stays the same, you can see down beneath here. But that the atomic number, Z, has decreased by 1. And therefore there must be a minus 1 over this side in order that 7 minus 1 gives you 6. And that has to be a beta particle. Okay, the third one then, and I'll just scan out again, is gamma decay. So gamma decay is high energy, very high energy, electromagnetic radiation. I'm just going to write EM. In other words, it's a wave. It's a wave and it is a particle, which is very strange. But description of the decay: nucleus becomes more stable, and it does that to give out gamma radiation, or it gives out gamma radiation to do that. Now, it doesn't change. The nucleus does not change into another atom. So be aware of that. The nucleus doesn't change. Effect on A and Z and a description. Now, this is probably quite unrealistic, but if you had carbon-14 and it was quite unstable, it would then decay to give you gamma radiation, but nothing about the carbon would change because the numbers on the gamma are 0 and 0. So 0 plus 14 gives you 14, 0 plus 6 gives you 6. So A stays the same and Z also stays the same. Okay, these are a couple of wee radiation questions for you. It says, what are the 3 types of radiation? So they're alpha, beta, and gamma. Which is most penetrating? Now, gamma is the most penetrating and the most dangerous. Why is radioactive waste not stored in permeable rock? So if water passes through, as it does, then it will become contaminated. And then it might get into our water system, our water supply. And that's a problem. Why should nuclear power stations not be situated in geologically active regions? In other words, regions where there are earthquakes and volcanoes. An earthquake could damage a nuclear power station, and that could be potentially very dangerous. And could cause a leak.